Hello class, welcome to another lecture in soil mechanics. So we are now in the fourth chapter, which is the permeability and seepage. So we have the following contents, but first in this lecture video, I will be only discussing the topics for permeability, which is the definitions, the hydraulic reagent, Darcy's law, factors affecting permeability, the laboratory and field determination of the coefficient of permeability, and the permeability of stratified soils. So the topics for seepage, namely from seepage force to the design of filters, will be discussed in the next videos to come. So in our second chapter, we have learned that the soil is made up of solid particles and in between those particles are voids that is either filled up with water or air. And when those voids are interconnected, the water is allowed to pass through the soil or flow through the soil sample. So that's when we can say that the soil is permeable. So because permeability is the ability of a substance to allow gas or liquid to flow from it, and in our case, in the subject, the substance we are referring to is soil, and the liquid referring to is water. Next is seepage. So seepage is the flow of water through soil. And the hydraulic conductivity or coefficient of permeability is a parameter of soil that determines how fast or how much water can pass through it per unit or per unit of time. So you have been familiar with the Bernoulli's equation since you are finished with your hydraulics class. And in this equation, it states that the total head is equal to the sum of the pressure head, the velocity head, and the elevation head. But in this case, for soils, the velocity head can be ignored since it is very small. And therefore, you will arrive with this equation. So the total head is equal to the pressure head plus the elevation head. And rearranging for points A and B, you will get this equation. And the hydraulic gradient can now be written as the delta H over L. And notice that L, or always take note rather, that L is always parallel to the direction of flow. So now let's proceed to Darcy's law. So this law states that the discharge velocity V bears a linear relationship to the hydraulic gradient I. So it governs the movement of fluid in a given substance. And this is according to the experiments of Henry Darcy. So he is a French engineer. And mathematically, we can write the discharge velocity V is equal to the hydraulic conductivity K times the hydraulic gradient I. So let us now discuss the discharge velocity V and its relationship to the seepage velocity. So when we say V sub S, that is the actual or the seepage velocity. So next is the discharge velocity. So simply V, no subscript. So this is the discharge velocity. So how are these two related? So so our discharge Q is equal to, or sometimes denoted as small letter q. So this is equal to the area times the velocity. Or if we are using the actual or seepage velocity, V sub S, our area is just simply the area of the voids. And noting that the gross area is equal to the area of voids plus the area of solids. Again, I would like to emphasize the gross area is to the discharge velocity. While when we are talking about the seepage velocity, we are only considering the area of voids. So let's proceed. So these two is equal to each other. So we can write A gross area times the discharge velocity is equal to the seepage velocity times the area of voids. And we can isolate the seepage velocity. So Vs is equal to the gross area times the discharge velocity all over the area of voids. And we can further expound. So the gross area is the area of voids plus the area of solids times the discharge velocity all over the area of voids. And let's convert this to volume. So what we're going to do is we multiply the length over length, which is okay because L over L is equal to 1. So we are multiplying this side of equation to 1. So this will now become the volume of voids plus the volume of solids all over the volume of voids times the discharge velocity. And we can rewrite this one. So 1 plus Vs all over Vv times the discharge velocity. And this will look familiar to you, of course, in our soil mechanics. So this is equal to the void ratio. The reciprocal of the void ratio, 1 all over E. And so let's rewrite this. So 1 plus E all all over E, or 1 over 1 1 1 plus E over E times the um, discharge velocity. So this is equal to V all over N. So we can write that the discharge velocity Vs is equal to the the seepage velocity V sub S is equal to the discharge velocity all over the porosity. So let's have an example problem. So the hydraulic conductivity of the permeable soil underlain by an impervious layer is 5.3 times 10 raised to negative 5 meters per second. Determine the rate of seepage through it per meter width if h is equal to 3 meters and the angle alpha is 8 degrees. So for the solution, so our this so Q is equal to, or the rate of seepage is equal to the discharge velocity times the area or gross area. So we are using the gross area because it is very hard to determine the area of the voids in this problem. And we can, from Darcy's law, so V is equal to the coefficient of conductivity times I, the hydraulic reagent. In this case, I will write this as delta H all over L times the area. So let's denote this one as the thickness T. So your thickness T is perpendicular to the direction of flow. So thickness and width. So this is our discharge velocity and this is our area. So we know the hydraulic conductivity. So for our delta H, over L, this is simply, so because this is our L, always note that L is parallel to the direction of flow and this angle here is 8 degrees. So when you write sine 8 degrees, this is simply our delta H all over L, or our hydraulic gradient. Yeah. And as for our thickness, so our thickness T, we can write that as, so this one can be written as cosine 8 degrees. So because this is our thickness, this is our thickness, so we can write cosine 8 degrees is equal to t all over height h. And then there is no problem for the width because the problem indicates that per meter width. So substituting this, so you can write 5.3 times 10 raised to negative 5 meters per second times sine 8 degrees times thickness t cosine thickness t is equal to h cosine 8 degrees, in which h is equal to 3 meters times d with 1 meter. So you can get q is equal to 0.0789 cubic meters per hour per meter width. So another example, we are asked to calculate the flow rate in cubic meters per meter length through the permeable layer shown. So h is equal to 8 meters, h sub 1 is 3 meters, h is small letter h is 4 meters, and the length L is equal to 50 meters, and alpha is 8 degrees, while the coefficient of permeability is 0.08 centimeters per second. So for this solution, K is, we will use again Q is equal to K I or delta H all over L times the area, which is the width times the thickness T. So this is known for delta H. This is equal to 4 meters. And then how about our L? So this is not parallel. This is not parallel to the flow. So we have to calculate this length. The length of this one, so let's denote as L prime for the sake of this problem. So our L prime is the one parallel to the direction of flow. So we can write cosine 8 degrees. So this is our 8 degrees. So it's cosine. So cosine 8 degrees is equal to L all over L prime. And our L prime is equal to 50 all over cosine 8 degrees. And the width is 1 meter, while for the thickness T, so this is equal to 3 meters cosine 8 degrees. So same for the previous problem. So this is our thickness T, which is perpendicular to the direction of flow. So we can now substitute. Q is equal to 0.08 centimeters per second times delta H, which is equal to 4 meters or 400 cm, all over L prime, which is 5,000 centimeters, all over cosine 8 degrees times 300 centimeters times cosine 8 degrees times 100 centimeters. So our Q is equal to 1. 188.2811 centimeters per so we can cancel this one and we will remain with cubic centimeters per second. So if we are going to convert this in meter, you will get 1.88 to 8 cubic meter per second. So simply divide this by 100 raised to 3 to get cubic meter per second. So now let's proceed to the factors affecting permeability. So there are 10 factors which affects the permeability of a soil sample. First is the soil particle. So if the soil is coarse-grained, the permeability is more, and if it is fine-grained, the permeability is low. So this is because coarse-grained soils tend to have more voids than fine-grained soils. Next is the specific surface area of the particles. So the higher this specific surface area, the lower the permeability. Next is the shape of the soil particle. So the permeability is more for soils with rounded particles than those with angular shape. So next is the void ratio. So it is said that generally the permeability increases with void ratio, but that is not always applicable to all types of soils. So for clays in particular. And next is the soil structure. So the permeability is more for flocculated structure and less for dispersed structure. So the permeability of stratified soils also varies according to the direction of soil. So the permeability is more in parallel than in perpendicular flow. So this another factor is the degree of saturation. So for fully saturated soils, the permeability is more than partially saturated soil. This is because when some of the voids are filled with water, the water will have some trouble on displacing the air particles. So it is much easier for this water to flow if the soil is fully saturated for than partially saturated. So next is the water properties. So the properties such as unit weight and viscosity also affects permeability. But viscosity affects the permeability more because viscosity changes with temperature. Unlike the unit weight of water is always the same at any temperature. So again, the next one is the temperature. So the greater the temperature, the greater the permeability. So this is because the viscosity of water is less when the temperature is high. And the less viscous the water, the easier it is to flow through the soil. Next is the adsorbed water. So this is the water layer formed around the soil particle, especially in fine-grained soils. So if there is water formed around the fine-grained soils, the void spaces are reduced, and so is the permeability. And lastly is the organic matter. So the presence of organic matter decreases the permeability due to the blockage of voids. So now let's proceed to the laboratory and field determination of hydraulic conductivity. So we have two methods in determining the um, coefficient of hydraulic conductivity, or the hydraulic conductivity rather, for in the laboratory. So this is the constant head test and the falling head test. So in the field, the hydraulic conductivity can be determined by the pumping from wells. So this is similar from our hydrology class, the one we have discussed in the flow of groundwater. So this involves the unconfined and confined aquifers. So in the constant head test, this is the setup for the constant head test. So in this setup, the water supply at the inlet is adjusted in such a way that the difference of head between the inlet and the outlet, this one and this one, will remain constant. So when the constant flow rate is established, the water is collected in a graduated flask for a known duration. So how do we write this mathematically? So again, the discharge Q is equal to the area times the discharge velocity times time. And we can write or expound that this is equal to the area times the coefficient of hydraulic conductivity K times the head, or in this case, the difference in head is equal to H. So there is no problem here because this is constant. So, sorry. Let's write this as H, simply H. H all over L times time T. Sorry, I have made a little mistake. So this does not refer to discharge but the volume of water collected rather. So Q, volume of water collected. And because if this pertains to discharge, we do not have to multiply it by time. But again, in this equation, this Q here pertains to the volume of water collected. And solving for K, we can get hydraulic conductivity is equal to the volume Q times the length. So this is okay because this is our direction of flow downwards, which and L is parallel to the direction of flow. And the remaining variables, which is A is the area of the soil sample. And H, or the difference in head, and the time T. Okay. So let's have an example problem. In a constant head permeability test, the length of the specimen is 30 centimeters, and its cross-sectional area is 177 square centimeters. So the setup has a constant head difference of 50 centimeters, and the water collected in 5 minutes is 350 cubic centimeters. Determine the hydraulic conductivity of the soil sample. Again, the hydraulic conductivity K is equal to the volume collected times the length of the specimen all over the cross-sectional area, the constant head difference, and the time T. So let's solve this problem in terms of centimeters per second. So our volume is 350 cubic centimeters times the length of the specimen, 30 centimeters, and cross-sectional area, 177 square centimeters, times the constant head, which is 50 centimeters, and the time T, 5 minutes, 5 minutes times 60 seconds. So we can get 3.9548 times 10 raised to negative 3 centimeters per second. So now let's proceed to the falling head test. So in this setup, the water from a standpipe is allowed to flow through the soil, and there will, since it is not made to remain constant, there is a head difference after a certain time. So the initial head is H1 and the final head is H2. And in this setup, the coefficient of hydraulic conductivity or the hydraulic conductivity or the coefficient of permeability K can be determined by using K is equal to AL over AT times the natural logarithm of H1 all over H2, wherein A is the cross-sectional area of the standpipe, this one, and A is the area of the specimen, and again, L is the length of the specimen, and the H1 and H2 are the initial and final head respectively. So let's have an example problem. So the length of a soil specimen in the falling head test is 8 inches. So the area of the soil specimen and standpipes are 1.6 and 0.06 respectively, square inches respectively. So if the initial head is 20 inches and the head after 3 minutes is 12 inches, calculate the hydraulic conductivity of the soil. So again, K is equal to area of the standpipe times the length of the specimen all over the area of the soil specimen times the time elapsed times the natural logarithm of the initial head all over the final head. And this is equal to 0.06 inches squared times the length 8 inches all over 1.6 inches times 3 times 60 seconds times the natural logarithm of 20 inches all over 12 inches. So this is equal to 8.5138 times 10 raised to negative 4 inches per second. So now that we have discussed the permeability test, but in the laboratory, so let's now proceed to the field determination of hydraulic conductivity. So we have two cases. First is the unconfined aquifer and the second one is the confined aquifer. So for an unconfined aquifer, the hydraulic conductivity can be determined by using this formula. Take note that in this formula, Q is the rate of pumping or the discharge. And R1 and R2 are the radius or the distance of the observation wells. So when the So this is also applicable to the heads. So 1 refers to the farther observation well, and 2 pertains to the nearer observation well. So, in an unconfined aquifer, so the term itself says that it is unconfined, so meaning there is no impervious layer above the water table or the piezometric reading. So for the next one is the confined aquifer. So this can be determined by using this formula. K is the hydraulic conductivity, Q is the rate of pumping, and R1 and R2 is the distance of the test wells from the pumping well. The distances of the observation wells from the pumping well. 2 times pi, and h is the thickness of the aquifer, and h1 and h2. So these are the heights. So the transmissibility T is also given by this formula. But this time, Z2 and Z1 is the drawdown. So, drawdown, in Tagalog, yung ibinaba niya dito sa points na to with respect to the piezometric level before pumping. So, let's have an example problem. So, in this problem, there is a 500 mm diameter test well, and it penetrates 30 meters below the static water table. So after 24 hours of pumping at 80 liters per second, the water level in an observation well, this is well, not wall, at a distance of 100 meters from the test well is lowered 0.50 meters, and the other observation well at a distance of 40 meters from the test well, the drawdown is 1.1 meters. So we are asked to calculate the rate of flow in cubic meters per day, the coefficient of permeability, and the drawdown in the test well. So this is an example of an unconfined aquifer. So this is our initial, and for example, this is our test well. So in this distance are the observation wells. So this is the initial water level. And this is the ground surface. And after some time, this is the initial water level, it will go down. And yan. Just like in the drawing, so we will have drawdowns here. So Z1 and Z2, and let's denote Z as the drawdown in the test well. But first, we are asked to find the rate of flow in cubic meters per day. So we will simply convert 80 liters per second to cubic meters per day. So 80 liters per second times 1,000 liters is equal to 1 cubic meter times 3,600 seconds is equal to 1 hour and 24 hours. And 24 hours is equal to 1 day. So, liters, sorry. So, we can cancel seconds and hour. So, we can get 6,912 cubic meters per day. B. So, next is we are asked to find the coefficient of permeability, K. So, this is equal to the pumping rate, 6,912 cubic meters per day times the natural logarithm of the two distances, 100 meters all over 40 meters all over pi times, since the initial height, so this is so somewhere below here, this is, but these two are different levels, so let's assume that this is the 30 meters, and therefore our H1 is equal to 30 meters minus the drawdown, 0.50 meters. So this is 29.50, and H2 is equal to 30 minus the drawdown, 1.1. So this is equal to 28.90 meters both. And from the formula, H sub 1 squared, so 29.50 squared minus 28.90 squared. So we can cancel. So we can get 57.53 meters per day. And lastly, we are asked to determine the drawdown in the test well. So we can use this formula also to determine the drawdown in the test well. So this is Z based on our figure. And we now know that the hydraulic conductivity is equal to 57.53 meters per day. And we will only consider this portion. So our discharge is 6912 meters per day, cubic meters per day rather. Then for our radiuses, so this is equal to 29, sorry, we are talking about the radius. So this is equal to 40 meters all over the, so since our test well is 500 mm in diameter, we can write 0.25 meters or just the radius of the test well. And then all over pi times the 28.90 meter squared minus our h sub 2 this time. So solving for h sub 2, we can get h sub 2 is equal to 25.32 meters. So this is our h sub 2 for problem number for the third unknown. And to get the drawdown, so this is simply 30 meters minus 25.32. So this is equal to 4.68 meters. So now let's proceed for the final topic of permeability. So this is the permeability of stratified soils. So when we say stratified, the soil is made up of different layers. So in each layer, there is a different type of soil. So with that, each soil has a different property, and one of those properties is the hydraulic conductivity. So for the layered soils, we have to find the equivalent horizontal hydraulic conductivity and the equivalent vertical hydraulic conductivity. So how do we know if it's horizontal or vertical? So it is simply the direction of flow with respect to the layers of the soil. So for horizontal flow, this is our soil layers, and the direction of flow is parallel to the soil layers. So for each layer, we have the horizontal hydraulic conductivity, and then we have their respective thickness, H1, H2, H3, or H and so on, and the total height of the sample, which is the summation of each. So to get the equivalent horizontal hydraulic conductivity, so this is the summation of the individual hydraulic conductivities of the soil times their respective height all over the summation of the heights or thickness. So this one. Just use this formula. So KH1 times H1 plus KH2, H2, so on, all over the total H. So that is the equivalent hydraulic conductivity in the for horizontal flow. So next is for vertical flow. So in this one, the equivalent vertical hydraulic conductivity is equal to the total H all over the summation of the thicknesses H all over the hydraulic conductivity, or H all over H1 over KV1 plus H2 over KV2, and so on. So let's have an example problem. So we are asked to find the ratio of equivalent hydraulic conductivity for a stratified soil. So these are the soil properties. So when we, in this problem, the equivalent hydraulic conductivity is given by the equivalent horizontal all over the equivalent vertical. So in order to get this, we have to get this 2. So the equivalent for the horizontal is equal to 10 raised to negative 4 times 150 cm plus 3.20 times 10 raised to negative 2 times 300 plus 4.1 times 10 raised to negative 5 times 200 cm. So I have omitted the units in order to write less in the formula because we are a bit lacking in space. So, but this is in terms of centimeters and centimeters per second. And this is already total area, total thickness rather. So 150 plus 300 plus 200 or 650. So we can get 0.0148 centimeters per second. And then for the vertical equivalent, so we can write 650 all over 150 over 10 raised to negative 4 plus 300 all over 3.20 times 10 raised to negative 2 plus 200 all over 4.10 times 10 raised to negative 5. And this is equal to 1.0176 times 10 raised to negative 4 cm per second. What I did is store these values in the calculator. So that I will arrive in the exact answer And then our Q equivalent is equal to Q equivalent horizontal over the equivalent in the vertical flow, or 0.0148 1.0176 times 10 raised to negative 4 and this is equal to 145.4851. And this one is unitless because this is the ratio. So that's all for permeability. We'll discuss the seepage in the next videos to come. And if you want some further readings regarding the topics I have discussed, you can use the references I've used. So this is the Principles of Geotechnical Engineering by Braham Das. So that is a very good book when you're studying geotechnical engineering. And the factors affecting the permeability of soil, so that is from the constructor.org. And so you can also subscribe to my channel so that you will be notified whenever I will be uploading new videos. So again, thank you for learning with me and see you in the next video.